All right, now let's take a look at section 1.6 and talk about more equations. The title of this section is a little ambiguous. It's a little vague, more equations, because we're going to talk about several equations, not just one type. We're going to begin with polynomial equations. Now, polynomial equations are going to be central to the study of this course, mostly because, well, the big secret of algebra is either everything is a polynomial, or if you play with it a little bit, you can turn it into a polynomial. So regardless of whether or not we start with a polynomial equation, eventually a polynomial equation will become central to whatever it is that we're doing. Before we start looking at other types of equations, let's remind ourselves of some of the basics about polynomial equations. The simplest polynomial equation you can think of is a linear equation. Say, for example, you have 2x minus 1 is equal to 0. Without any exponents or without any other issues, radicals, rational expressions, or anything of that nature, these are very simple to solve because all you need are the four basic operations. You add to get rid of subtraction. That'll give us 2x equals to 1. And then you can divide both sides by 2. That way division and multiplication simplify out to give us x equals to 1/2. And there's our solution. Anytime you have a polynomial equation that is not linear, that your power is bigger than 1, you essentially want to break it down so that you have several versions of this simple kind of equation. We do that by factoring. So, for example, let's say we had something like 3x times 2x plus 5 times x minus 4 is equal to 0, like this. Right? In this equation, notice that the factoring's already been done for us. Once the factoring's been done, is just as simple as this one, albeit with more parts. Because once something has been factored, we can say if the product of these three factors is equal to 0, then one or more of these must have been equal to 0. So here we can solve each one on its own as if it were just a simple problem, a linear problem like this one up here, rather than something more complicated with more pieces. So instead of having one big problem, this breaks into 3 smaller ones, like this. Here, I can divide both sides by 3, and that gets us our solution, x is equal to 0. Of course, that's not the only solution. Here, I can subtract 5 from both sides to give me 2x is equal to negative 5. And then if I divide both sides by 2, that'll isolate my x to give me x is equal to negative 5/2. And here, I can go ahead and add 4 to both sides to isolate my variable. That'll give me x is equal to positive 4. And here, this gives me 1, 2, 3 different solutions to my problem. Now, if your problem is already factored, that's great. You can simply solve each one by setting equal to 0. But if your polynomial equation is not factored out, well, then that's up to us to do. Note that in the case of a quadratic equation, you will have other options. You could also use the quadratic formula, or you could extract and complete the square. But in the case of something bigger than a quadratic, something with a third power, fourth power, or fifth power, that's not an option because those aren't quadratic. So factoring is something that we have to fall back on. All right? So let's consider another equation. Let's consider the polynomial equation. Let's see. X to the third plus 2x squared equals 25x plus 50. Okay. One thing to note about this is this equation is not equal to 0. Whenever we have a polynomial equation, generally what we want to do is we want to make one side equal to 0 so that we can factor. The exception of that being the linear equation, but because with a linear equation, no factoring is necessary. Here, we're simply trying to move these terms this way so that we can isolate our x. But if it's not linear, for example, here or here, your first step is to make one side equal to 0. So let's go ahead and do that before we start any factoring. Let me go ahead and subtract my 25x from both sides of the equation. And let me go ahead and subtract 50 again from both sides of the equation. So this problem can be written as x to the third plus 2x squared minus 25x minus 50 is equal to 0. Okay. So now let's review some factoring techniques. We note that this has 4 terms. 1, 2, 3, 4 terms in our polynomial. Whenever you have something that has 4 terms, one factoring technique that may work, now it's not guaranteed, but there's a good chance it's going to work here, is factoring by grouping. Let's remind ourselves of how that works. Whenever we factor by grouping, we take the first 2 terms and bunch them together. So here I'm going to write x to the third plus 2x squared in parentheses. And then you take your second set of terms and bunch them together. So negative 25x minus 50. Here I'm going to put a plus sign in between because without the plus sign it would look like these are being multiplied together, right? Here there's no multiplication between these. It's all addition and subtraction is equal to 0. So now the next step is look at just the first 2 terms. Ignore these for just a moment. Looking at just these 2, we're going to take out the common factor. Notice that both of these can be divided by x squared. So x squared is our common factor. And if we actually go through and divide those by x squared, we're left with just an x and just a 2. Over here, we have a common factor as well. We notice that both of those terms can be divided by 25, all right? But also they both have a negative. So let's say negative 25 is our common factor. Here we can write plus negative 25, but plus a negative, we can just write that as minus. You can write plus a negative 25 if you like, but most people would just write minus 25. If we now divide this by negative 25, we're left with just an x. And if you divide this by negative 25, you're left with plus 2. Notice now that you have plus 2 as a common factor to both parts of that expression. Oh, okay, so you can factor it out the way you usually handle common factors. X plus 2 is a common factor. If you factor out x plus 2 from here, you're left with an x squared. If you factor out x plus 2 from here, you're left with minus 25 is equal to 0, just like that. If you're not sure you did that correctly, you can always multiply it back out. That will be x to the third plus 2x squared. Okay, so far those are good. And then minus 25x and minus 50. Yeah, that works out just fine. Here, this can be factored a little bit further. This is the difference of squares. After all, there's something you can square to get x squared. It's the variable x. And there's something you can square to get 25. That's the number 5. Whenever you have the difference of squares, it factors into the product of conjugates. So here one would have a plus, one would have a minus. And again, if you're not sure about that, you can always check that by multiplying it back out. That's x squared minus 5x plus 5x would just give you 0. And then 5 times negative 5 is negative 25. So that would be x squared minus 25. And now, once that's been factored out, we get to do what we did before. And that's each piece on its own can be solved by setting it to 0. So here we can say, okay, now if x plus 2 is equal to 0, we get a solution. If x plus 5 is equal to 0, we get a different solution. And if x minus 5 is equal to 0, we get a third solution. So here, let's subtract 2 from both sides, and that gets us a solution. If we subtract 5 from both sides, that'll get us a solution. And if we add 5 to both sides, that'll get us a solution as well. So here, this will be x equals negative 2. Here, this will be x equals negative 5. And this will be x is equal to positive 5. And these are going to be our solutions. Those are all examples. Yeah? All right. So before we continue to other types of equations, give this a try. Take the following polynomial equation and go ahead and solve. Let's do 2x to the fourth minus 128, that should be equals negative 128x, like that. Right? This one's going to be a little bit different than the previous one. Notice this has fewer terms. It doesn't have 4 terms, so you're not going to be using factoring by grouping, but you'll be using some other factoring techniques that you've had before this course. Go ahead and pause the video, give this a try, and whenever you get an answer, go ahead and unpause the video, and we'll go through it together. All right, so let's take a look here. We want to make one side of our equation equal to 0 so that we can factor out on the other side. So let's go ahead and add 128x to both sides of our equation here. And this will give us 2x to the 4th plus 128x is equal to 0. So here, factor by grouping isn't going to work because we don't have enough terms. Notice, though, that even without grouping, we still notice we have a common factor. The point of grouping is to see if we have a common factor for some part of our polynomial. Here, we don't need to group to find a common factor. There's a common factor already. Note that these numbers are both even, which means I can divide by 2. And here, both of these have an x. Now, this one has more than just one x, but they both have at least one. So a common factor is going to be 2x. One word of warning, some people divide both sides by 2x. Don't do that. If you divide by 2, okay, that's fine because it's a constant. But if you divide by x, what you're saying is I'm dividing by some number that I don't know. And remember, not all numbers can be divided by, in particular 0. If you divide by x, what's going to happen is if 0 was one of your solutions, which it turns out for this problem it is, you're going to be losing one of your solutions. In other words, at the end, you're going to have an incomplete answer. So here, you might be tempted to say, oh, I can divide both sides by 2x, so let me divide both sides by 2x. Don't do that, because whenever that happens, you may lose some solutions. What you want to do is instead of dividing by that, you want to factor it out. That way it's been removed from the terms, but it's still part of the problem. So here we can write this as x to the 3rd plus 64. Okay, so now here we have x to the 3rd plus 64 is equal to 0. Here, we can factor this. This can be factored out. This is the sum of cubes. Now, some may not remember the sum of cubes. There are some factoring techniques that we use all the time, like taking out a common factor or the product sum method, things like that. But there are some other techniques that are a little more obscure, that they don't come up as often. So for that, let's remind ourselves of how the sum of cubes works. Also, remember that you can look up our handout on factoring techniques. It's labeled factoring. It's under the prerequisite materials section. And it'll also give you some more examples of some factoring techniques, which include sums and differences of cubes. But for now, instead of going over and looking that up on our prerequisites page, let's just go ahead and remind ourselves of what that looks like here. Whenever you have the sum of 2 cubes, in other words, something to the 3rd power plus something else to the 3rd power, that can factor as a plus b times a squared minus ab plus b squared, where a and b are the things that you cubed to get this and to get this. In our particular example, x is the thing that's being cubed to give us x to the 3rd power, and 4 is the thing that's being cubed to get us 64. 4 times 4 is 16, times 4 more is 64. So our a is being replaced by the variable x, and our b is being replaced by the number 4. So here that would be a plus b, okay, x plus 4, times a squared, okay, that's going to be x squared, minus a times b, okay, 4 times x, plus b squared. Okay, well, that's 4 squared. Okay. And then here, 4 squared can be written as 16. So we can write this as x plus 4 times x squared minus 4x plus 16. Just like that. Where, again, note, this x is our letter A, and here this 4 is our letter B. So that sum of cubes, that x to the third plus 64, can be written as all this stuff here. So that's going to be 2x times x plus 4 times x squared minus 4x plus 16 is equal to 0. All right. Here, I would like to factor this a little bit more, but I notice that I don't think I can. I don't have any common factors here. And I can't think of any numbers that multiply to give me 16 and add up to give me negative 4. Fortunately, I don't need to factor this one to find the solutions to it because it's a quadratic. And with a quadratic, I have other options. For example, extracting and completing the square or using the quadratic formula. All right? So here, I can go ahead and solve each one of these on their own. I can say, all right, let me take 2x and set that equal to 0. I can take x plus 4 and set that equal to 0. Or I can take x squared minus 4x plus 16 and set that equal to 0. These two are nice and short. I can just go ahead and divide both sides by 2 here. And over here, if I subtract 4 from both sides, in both cases, I isolate my x. That's 1x equals to 0. Okay, that's one solution. And here I have x is equal to 0 minus 4, or in other words, negative 4. So those are two solutions. I have one more equation here that I can solve. That's a quadratic equation. Again, factoring doesn't look like it's going to work on this one, but I have other options. Right? I can always extract and complete the square, or I can always use the quadratic formula. Here I'm going to go ahead and complete the square. I'm going to go ahead and say, all right, let me take those two terms and bunch them together. Let me push that 16 off to the side, equals to 0. Okay. I want to factor out the lead coefficient, but I notice the lead coefficient is 1, so that's not going to change anything. I'll go ahead and write the number 1 here, but it doesn't actually change anything. So now I'm going to take this number, cut it in half, that's negative 2, and then squaring negative 2 will give me a positive 4. Negative 2 times negative 2 is positive 4. Then I'll subtract 4 there to balance out that extra plus 4 that I just introduced. So now let me write this as 1x squared minus 4x plus 4. Now let me kick this one out and join it with this one. So here, negative 4 times 1 is still negative 4 when it comes out of the parentheses. But now, this can factor out. What two numbers multiply to give me 4 and add up to give me negative 4? That's going to be negative 2 and negative 2. So that's going to be x minus 2 times x minus 2, or in other words, x minus 2 squared. And these are just regular numbers. 16 minus 4 will give me 12. Okay. Here, if I subtract the 12 over to the other side, that'll give me negative 12. All right, so that's going to be x minus 2 times x minus 2, which is x minus 2 squared. I subtracted the 12 from both sides to give me x minus 2 squared equals negative 12. And now I can take the square root of both sides. Remember, when you take a square root, you have two values, a positive and a negative. So that's going to give me x minus 2 is equal to, well, here I can simplify this, plus or minus. The square root of negative 12 can be written as the square root of negative 1 times 4 times 3, which is equal to plus or minus the square root of negative 1 times the square root of 4 times the square root of 3. And here that's going to be I, that's the imaginary unit. That's going to be 2. So 2 times I times the square root of 3. So x minus 2 is equal to plus or minus 2I root 3. And finally, go ahead and add that 2 over to the other side, and you get your result. And it goes away. So here we get x is equal to 2 plus or minus 2I root 3. Right. Notice this is actually two solutions, 2 plus that, and then separately 2 minus that. But it's common and acceptable to write it all together as a plus or minus. And that is our result. Or rather, those are our results. Those are our solutions to that polynomial equation. One thing to note, this was a polynomial equation. The power was 4. In the end, we get, well, remember, those are two solutions. So 2 3, 4. The power was 4, and you have 4 solutions. Over here, we had an equation that had a power of 3, and you had 3 solutions. For now, that's just something to notice. It's going to turn out to be very important later on down the line. All right, now let's take a look at another kind of equation. Now you might say, well, wait a minute, are we really done with polynomial equations? Well, no. But the thing is that everything else that we see in this section, and in fact in this chapter, and in fact in this course, it's always going to come back to polynomial equations. So that means that here, we want to remind ourselves of a few basic things, namely some factoring techniques. But we're going to have plenty of opportunities to practice polynomial equations, factoring, and solving, because those are going to show up no matter what our problem looks like. You'll see that here in our next example. So let's start off with something that looks different. Let's talk about rational equations. All right. A rational equation is an equation that has a rational expression in it, or at least one rational expression. The word rational comes from the word ratio, R-A-T-I-O, which is an old word for fraction. So basically, rational equations are fractional equations. They're equations that have fractions in them. Those fractions, although they can involve regular real numbers, usually what we want are variable fractions. Fractions that have variables in the numerator and or denominator. So for example, let's go ahead and try, let's try this one. I'm going to take 4x over x minus 5 minus 1 over x plus 1 equals 3x squared plus 3 over x squared minus 4x minus 5. Okay. All right, so first of all, notice that these are rational expressions. They're expressions that have they're expressions in a fractional form. You have a numerator and a denominator, and sometimes you have whole numbers, and sometimes you have variables in each of the positions, numerators or denominators. Notice, however, that these numerators and denominators, whether they have variables or constants or both, are basically just polynomial expressions. That's linear, that's linear, that's quadratic, that's quadratic, that's a constant, just a regular number. So within these rational expressions, you see polynomial expressions. In order to solve a rational equation, you're going to notice a pattern that's going to pretty much follow us through the rest of this course. If something is a polynomial to start off with, then we solve it by factoring. In the case of a quadratic, we have a couple of extra options, but generally speaking, factoring is the way we want to go. If something is not polynomial, what we're going to do is we're going to take steps to turn it into a polynomial equation. Not just an equation that has polynomial expressions inside of it, but actually a polynomial equation. Once we have a polynomial equation, then we'll solve it the way we always solve polynomials, through factoring and maybe the quadratic formula if it's appropriate for that particular polynomial. So for a rational equation, the first thing you're going to want to do is you're going to want to take your denominators and you're going to want to factor them. Now, some expressions just don't factor. They're already in the simplest way they can be written. However, other expressions can be factored. You might look at the numerator and say, well, what if I factor the numerator? There's nothing wrong with that, but it's not necessary for this kind of problem. All right? So here, I'm going to rewrite this as 4x. I'm going to write that with minus 1, and I'm going to write this as 3x squared plus 3. The numerators, maybe they can be factored, maybe they can't. I'm not really going to worry about that. What I'm going to rewrite are the denominators. Those that can be factored, I need to factor. If they can't be factored, well, then we don't worry about those. Notice that this is linear, first degree, and it doesn't have any common factors. If something is first power and doesn't have any common factors, there's nothing you can really do to factor it. Same thing for this one. This is linear, right? First power, and there's no common factors between these terms. So there's nothing you can really do about it. Just leave it alone as x plus 1. But now this is definitely not linear. It's quadratic, which means we can probably factor this out, yeah? Here, we can write this as x times x, because that's what's going to give us x squared. And now we want two numbers that when multiplied together give us this negative 5, when added together give us this negative 4. Well, that's going to be negative 5 and positive 1. After all, negative 5 times positive 1 is negative 5. Negative 5 plus 1 is negative 4. So your first step is factor out all of the denominators, or at least all the ones that can be factored. The next thing we want to do is we want to give these denominators a common denominator. We want to give these expressions a common denominator. Notice that this would look just like that if it had an extra factor of x plus 1. So that's what I want to do. I want to multiply this by x plus 1. That way this denominator and this denominator match. But this is a fraction. Whatever I do to the bottom, I got to do on top. Here, I'm going to do the same thing. I'm going to say, okay, this would match this one if it had an extra x minus 5. Okay, so let me go ahead and multiply that by x minus 5. And x minus 5, just like that. And now all three of these have the same denominator. Okay, so now I can write this as, well, let me multiply those. 4x times x is going to be 4x squared. 4x times 1 is going to be 4x over that common denominator. I'm not going to worry about multiplying this out, and you'll see why in just a moment. So it's not going to matter. Okay, minus, here I have 1 times x. It's going to give me x. And 1 times negative 5 is negative 5 over, and again, x minus 5 times x plus 1. And I'm not going to bother multiplying those denominators because in a moment you'll see it won't matter. And here I have 3x squared plus 3 over x minus 5 times x plus 1. Just like that. All right. Now, notice that these are common denominators. What that means is we don't have to worry about what the denominators are anymore. Think about what happens when you add and subtract just regular fractions. If you have 2 over 7 plus some other number is equal to 5 over 7. Here, once I have a common denominator, I don't really worry about the denominators. If I say 2 over 7 plus something over 7 is equal to 5 over 7, well here, 2 plus 3 make 5, so that must be the correct answer. Notice if I changed all my denominators, that wouldn't make a difference. 2 over 17 plus 3 over 17 equals 5 over 17. 2 over 172 plus 3 over 172 is equal to 5 over 172. Notice that as long as the denominators are the same, we don't worry about them. All that matters is that the arithmetic in the numerators works out. The same thing's going to happen here. Once these have a common denominator, it doesn't matter what the denominators are. All that matters is that the arithmetic in the numerators works out. So what that means is, here, all I need to make sure is that 4x squared plus 4x minus x minus 5 equals to 3x squared plus 3. I need to make sure that's true. The denominators are already the same, so it's not going to matter what they are. Depending on what book you're looking at, some books will do this. They'll say, okay, let me go ahead and multiply both sides of the equation by the same thing. Let me multiply both sides of the equation by the common denominator. And by doing that, oh, that divides away. And all I'm left with is this expression. These divide away, and all I'm left with is that expression. And these divide away, and all I'm left with is that expression. So either way, you note that all that really mattered was the numerators. 4x squared plus 4x minus the quantity x minus 5 needs to equal to 3x squared plus 3. All right. So here, let me go ahead and simplify things out. Notice I have some like terms I can combine. I can write this as 4x squared. Here I have plus 4x, but then I have minus x. Okay, so that'll be plus 3x. And then here I have minus a minus 5. Well, that's going to be plus 5. All right. Well, notice that this went from being a rational equation down to being a polynomial equation. Okay, so now let's solve it the way we always solve polynomial equations. Let's make one side equal to 0 and then solve by factoring. First, let's make one side equal to 0. Subtract 3x squared from both sides. And let's subtract 3 from both sides. So those go away. And this is going to give me x squared plus 3x plus 2 is equal to 0. This is a quadratic equation. I could use the quadratic formula. I could complete and then extract the square, but both of those are way too long. This one's going to be a lot faster if we factor it. What two numbers multiply together to give me 2 and add up to give me 3? Well, that's going to be 2 and 1. All right? 2 times 1 is 2. 2 plus 1 is 3. And so I can solve each one of these on their own. I have x plus 2 is equal to 0. And then separately I can say x plus 1 is equal to 0. I can now isolate my variables to get my solutions. That goes away. And I'm left with x is equal to a negative 2. And over here I'm left with x is equal to a negative 1. Just like that. So starting from this equation, we come down. First of all, we find our common denominator. Once we have our common denominator, the common denominator doesn't bother us anymore. We can multiply out by the common denominator to eliminate the denominator and be left with only the numerators. But once you're left with just the numerators, those combine to give you a polynomial equation. And once that's a polynomial equation, we know how to solve that. Make one side equal to 0, and then factor and solve each one on their own. So these are our results. And they're wrong. I'm sorry, what now? They're wrong? Yeah, this is not correct. Oh, you made a mistake. Is that I must have made a mistake, right? That's the problem. Well, no. The thing is, I didn't make any mistakes. Everything that I've written here is absolutely correct. And yet these are not both the correct solutions. You say, well, why not? This has to do with the nature of a rational equation. Notice a rational equation is basically just the sum and difference of fractions. Okay, well, in other words, it's something divided by something else. Remember that there is one number that isn't valid as the denominator of a fraction. That's the number 0. I can't divide by 0. That's undefined. 1 over 0 is nonsense. 4 over 0, that doesn't make any, it doesn't mean anything. Okay, so what does that have to do with this problem? Well, notice that this denominator is variable. It can be any number, and that includes 0. If this denominator is 0, though, that can't be a solution, because a solution is a number that when you plug it into an equation makes the equation true. I can't have a true equation if part of my equation is undefined. So right here, notice what happens if I plug in negative 2. All right, negative 2 minus 5, well, that's negative 7. Okay, that's fine. I know how to divide by negative 7. That's not a big deal. If I plug in negative 2 right here, negative 2 plus 1 is negative 1. Okay, that's fine. I know how to divide by negative 1. That's not a problem. And same thing over here. Negative 2 squared is positive 4. Negative 4 times negative 2 is positive 8. So 8 plus 4 will give me 12. And if I subtract 5 from 12, that will give me 7. Okay, so if I plug in negative 2 into all of these, I get negative 7, negative 1, and 7. Okay, no big deal. Look what happens when I plug in negative 1. Negative 1 minus 5 is negative 6. Negative 1 plus 1 is 0. Oh, that's a problem. If I try to plug in negative 1 into this equation, I'm going to end up with a 0 denominator. Since a 0 denominator makes this expression undefined, that means I can't have a 0 denominator. That can't be a solution, which means this solution, even though everything we did to get here is correct, it's not valid. This has a name. This is called an extraneous solution. An extraneous solution is a solution that comes about through the algebra required to convert something that is not a polynomial into something that is a polynomial. Essentially, polynomial equations, by their nature, can accept any number. Any number can be added, subtracted, multiplied, or divided. But the equation that we started with has things besides just addition, subtraction, multiplication. In this case, you have division by a variable. So, in that process of converting something from rational into polynomial, you might introduce some solutions that shouldn't work, but it looks like they do. These are called extraneous solutions. They're basically fake solutions. They look like they work, but they don't. So we throw these away. Anytime you have an extraneous solution, it's something that looks like it's valid, but when you check it, it turns out that it gives you some kind of nonsense. Extraneous solutions will appear in other cases. There's going to be plenty of other equations that we see in this section, in this chapter, and in this course. And extraneous solutions appear for many equations, not just rational. So remember this word, and we're going to be seeing it over and over again throughout the semester. This one, on the other hand, did work. When you plugged it in, everything was fine. So this is the correct solution. So here you don't have two solutions. You had a fake solution. It's called an extraneous solution. It looks like it should work, but it doesn't. So this is the only real solution. This is the only correct solution. And there we go. Whenever you start with a rational equation, at the very end, whatever solutions you get, you should check them, because maybe they all work, or maybe some of them are extraneous, and you got to throw those out. So go ahead and give this a try. All right, let's see. Let's go ahead and try x over x minus 2 plus 2 over x minus 4 equals 4x minus 12 over, let's see, x squared minus 6x plus 8. Just like that. Go ahead and pause the video and give this a try. Find whatever solutions you can find, and don't forget to check. In the end, just because you have a solution doesn't mean it's correct. It may be extraneous. Once you have your solution or solutions, go ahead and unpause the video and we'll go through it together. All right, so let's take a look here. First of all, what we want to do is we want to factor our denominators, or at least the ones that can be factored. Here you notice these are both linear. They don't have any common factors, so there's nothing you can really do to those. But this one can be factored. So I'm going to write this as x over x minus 2 plus 2 over x minus 4 equals 4x minus 12 over, here, this factors by finding two numbers that multiply to give us positive 8 and add up to give us negative 6. Oh, well, that'll be negative 4 and positive 2. Negative 4 and negative 2. Negative 4 times negative 2 is negative 8. Negative 4 plus negative 2 is negative 6. So now what we want to do is we want to find common denominators for everything. Right? So here we can say, okay, well, if I just gave this one a x minus 4, that would be fine. X minus 4. There we go. Those have a common denominator now. This one, if I gave this one an x minus 2, it would look just like these do. Okay, so let's multiply by x minus 2. Just like that. And now you have a common denominator, which means we don't worry about the denominator anymore. All that matters is that our numerators should match up. So we have x times x minus 4 plus 2 times x minus 2 equals 4x minus 12. Okay, let's go ahead and simplify. Here I have some stuff that I can distribute and combine. That's going to give me x times x is x squared. X times negative 4 is negative 4x. 2 times x is 2x. And 2 times negative 2 is negative 4. Here I can combine these two. Negative 4x plus 2x is negative 2x. And now we have a polynomial equation. This polynomial equation we can now solve by setting one side equal to 0 and factoring out the other side. Of course, since that is quadratic, we also have a few other options. But first, we make one side equal to 0. So we can say minus 4x and plus 12 and plus 12. So this will give us x squared minus 4x minus 2x will give us minus 6x. 12 minus 4 is going to give us 8. It is equal to 0. Okay. Now we can solve by factoring. Notice that we have a quadratic. We can factor this by finding what two numbers, multiply to give us 8, and add up to give us -6. All right, well, that's going to be -4 and 2. Or -4 and -2. -4 times -2 is -8. Meanwhile, -4 plus -2 is -6. And now we can solve each of these. If x minus 2 is equal to 0, then I can add 2 to both sides, and that gets us x is equal to 2. Meanwhile, here, if I have x minus 4 is equal to 0, I can add 4 to both sides, and that'll give me x is equal to a positive 4. And these are my solutions. But again, these might be extraneous, so we have to check them. All right, let's start with the number 2. Okay, if I plug in the number 2, that's going to give me 2 over, let's see, 2 minus 2 is 0. 2 over 0, oh, right away, that's undefined. So here, this is extraneous. It looks like it should work as a solution, but when we go and check it, it doesn't actually work. So this one gets thrown out. Okay, so let's try 4 now. 4 over 4 minus 2. Okay, 4 minus 2 is 2. Okay, 4 over 2, that's fine. Let's plug in 4 over here. 2 over 4 minus 4. That's going to be 2 over 0. Oh, that doesn't work either. So here, 4 is also extraneous. Okay, so what does that mean? Well, that means that there's only 2 solutions that could have worked. But it turns out even those don't work. Well, that means that we don't have any solutions. Whenever we have an equation like this where all of our solutions are extraneous, that means this problem, this equation, has no solutions. These were the only 2 that might have worked, but even those didn't work. Okay, well then that means that this equation doesn't have any solutions. Whenever you have a rational equation, you may end up with several solutions that all work. You may end up with several solutions, only some of which work, as you saw in our previous example, only some of these work, and there is the possibility that none of them work. All solutions are extraneous, in which case that means you have no solutions. All right. So those are rational equations. Let's take a look at our next type of equation, which again you'll see looks different, but after a bit of manipulation, it's going to be handled the same way. We're going to turn it into a polynomial equation, and once it's polynomial, we're going to have a much simpler time working with it. All right? So for our first example, let's start off with one of the nice cases. What do you mean one of the nice cases? So here we're going to be talking about radical equations. Radical equations can be broken into a couple of different cases, meaning there's a few things that are, although they are all although they are all radical equations, they look a little different. And when they look a little different, they can be handled a little bit differently. We're going to start off with the nicest case, and that's the one where you only have a single square root in there. After all, that's what a radical equation is. It's an equation with a radical, in other words, a root in there. It is possible to have a radical equation with a third root or a fourth root or a fifth root. However, for the most part, you're going to see square roots, at least for our course. So let's take a look at an example. Let's start with this one. We're going to take the square root of 9x minus, let's make that a plus. 9x plus 19, and that's all underneath the square root, is equal to x plus 3. In a previous section, we saw that to extract the square, we took something that had a square on it and took a square root. That way the square and square root would simplify and give us just our radical, or our radicand, the thing underneath here. We're going to do the exact same thing, but in the opposite direction. In a previous section, we saw that a square root can be used to get rid of a square. Here we're going to do the opposite. We're going to use a square to get rid of a square root. So here I'm going to take both sides, and I'm just going to square. Okay. Now be careful when you're squaring. Here, the square of the square root gives me just the radicand, gives me just 9x plus 19. Over here, don't fall into the trap of saying, oh, I'm going to square the x and square the 3. That's not how squaring works. When you're going to square a binomial, remember that means you're multiplying it out. So here, let me go ahead and do that off to the side. If I'm going to have x plus 3 squared, that means I want x plus 3 times x plus 3, which means I have to distribute. So x times x will give me x squared. X times 3 will give me 3x. 3 times x gives me another 3x. And 3 times 3 will give me 9. So this will be x squared. 3x plus 3x will give me 6x plus 9. So be very careful with that. Don't fall into the trap of thinking that you can square by squaring each term. You multiply the whole thing out to get x squared plus 6x plus 9. All right, so now we have a polynomial equation. So we can go ahead and subtract this stuff over this way to make one side equal to 0 and then solve the remaining quadratic. So let me subtract the 9x and the 19 from both sides. That all goes away. And I'm left with 0 equals to x squared. 6x minus 9x is negative 3x. And 9 minus 19 is negative 10. And now we can solve that quadratic equation. Okay? Again, that's a quadratic, so we could complete and then extract the square, or we could use the quadratic formula. But you'll find that this one works very nicely if we just factor it. What two numbers can be multiplied to give me negative 10 and add up to give me negative 3? Well, that's going to be negative 5 and positive 2. Negative 5 times 2 is negative 10. Negative 5 plus 2 is negative 3. And so we get our results by setting each of these equal to 0. If I have x minus 5 is equal to 0, I can add 5 to both sides and get a result. On the other hand, if I have x plus 2 is equal to 0, I can subtract 2 from both sides and again get a result. So here I have x is equal to positive 5 and x is equal to negative 2. All right. Now, once again, you have to check these. Just like with a rational equation, you may have extraneous solutions, but for a different reason. With a rational equation, the reason you can have an extraneous solution is because when you plug in the number, it gives you a 0 in the denominator. And if you get a 0 in the denominator, the whole thing's just undefined. With a radical equation, the problem comes from a different source. Remember, square roots of negatives are complex numbers. So what will happen sometimes is you'll substitute in a value and you'll get a complex number equals to a real number. Well, that's not true. Other times, it'll be even more simple. You'll get a positive number is equal to a negative number. Essentially, by squaring both sides, what's going to happen is you will sometimes mess up the sign of your answer. Meaning, oh, I should have had a positive and I ended up with a negative. Okay, so then that doesn't work. Or you'll get, oh, I should have ended up with a real number and ended up with a complex number. And again, that won't work. So here we have to check these by substituting them back in. All right, so let's go and check. With a radical equation, you actually have to go through the whole thing. You actually have to go through and check everything. With a rational equation, it was just enough to make sure that the denominators weren't 0. With a radical equation, you can't take a shortcut. You really just, you got to check the whole thing. So here, let's go ahead and check to see if x equals to 5 is a valid solution. Maybe it is, maybe it's not. Let's go and plug it in right there into our original equation. That's going to be 9 times 5 plus 19 equals to 5 plus 3. And I'm going to put a little question mark over that because, again, I don't know if that's true or not. I don't know if those are equal. If they are equal, well, good. That means that that is our solution. If they're not equal, well, then we have to throw that one away. All right, 9 times 5 is 45, plus 19 is 64. So that's going to be the square root of 64. Here, 8 plus 3 is going to, 5 plus 3 is going to give me 8. And over here, if I take the square root of 64, that gives me 8. Yeah, that's right. 8 equals 8. That is a perfectly valid solution. So here, this one works out, and 5 is a correct solution. All right, let's try negative 2. Let's plug it in there. Let's see what happens. Let's go ahead and check x equals to negative 2. That's going to be the square root of 9 times negative 2 plus 19 equals to negative 2 plus 3. And let's see if that works. 9 times negative 2 is negative 18. Negative 18 plus 19 is just the number 1. That's the square root of 1. 3 minus 2, that's going to give me 1. The square root of 1 is equal to 1. Yeah, that's right. That is correct. So here, both of these are perfectly valid solutions. All right? So it's possible to have all of your solutions work. It's possible to have some of your solutions work, or maybe none of them work, in which case there's no solution. But in this case, yes, both of these are perfectly valid solutions, 5 and negative 2. Okay. Now, before we go on to a more complicated one, go ahead and give this one a try. Go ahead and solve the equation square root of 2x plus 29. Now, outside of the radical, we're going to have a plus 3 is equal to x. Just like that. Note that for you to be able to square both sides of the equation and for it to help you out, for it to make a difference, you need to have the radical by itself. So in this problem, the first thing you'd want to do is you want to move the 3 over and then square. If you square both sides now, you're not going to have such a nice simplification as you have up there. So the first thing you want to do is you want to go ahead and move that over and then proceed to do the simplification and the solving. Go ahead and pause the video. And once you get your solution, and again, make sure you check them. Just make sure they're valid. Make sure you don't have any extraneous ones. Go ahead and unpause the video and we'll go through it together. All right, so let's take a look here. Let's get rid of that plus 3 by subtracting 3 over this way. And this will give us the square root of 2x plus 29 is equal to x minus 3. Always make sure that before you square, your radical is by itself. Okay, so now we can go ahead and square both sides. Here, that's going to give me 2x plus 29. On this side, if I square x minus 3, once again, don't forget, to square something, you don't just square each part. You actually have to multiply the whole thing out. If you take x minus 3 times x minus 3, that'll give you x squared minus 6x plus 9. All right, x minus 3 times x minus 3. Distribute everything out to get that result. Now that I have a polynomial equation, I need to go ahead and make one of these sides equal to 0. Let me subtract 2x and subtract 29 from both sides to end up with 0 equals to x squared minus 8x minus 20. And now I can factor x squared minus 8x minus 20, two numbers that multiply to give me negative 20 and add up to give me negative 8. I can do negative 10 and positive 2. And so if x minus 10 is equal to 0, I can add 10 to both sides, and I get x is equal to 10. On the other hand, if I have x plus 2 is equal to 0, I can subtract 2 from either side, and I get x is equal to negative 2. So those are possible solutions. But again, we're not sure if they both work. We have to check them. So to check them, we're going to go back to our original equation and substitute, plug everything back in. All right, so let's take a look. Let's go ahead and check x equals to 10. That's going to be square root of 2 times 10 plus 29 plus 3 equals to 10. And let's see if that's true. 2 times 10 is 20 plus 29 is 49. So that's going to be the square root of 49 plus 3 equals to 10. Oh, but I know the square root of 49 is 7. So that can be 7 plus 3 equals to 10, which is absolutely true. 7 plus 3 is equal to 10. So 10 is a perfectly valid solution. Okay, let's go and check the other one. Let's go and check if x is equal to negative 2. All right, that's going to be square root of 2 times negative 2 plus 29 plus 3 equals to negative 2. All right. We're substituting in a negative 2 anywhere there was an x in the original problem. All right, negative 2 there and negative 2 there. All right, negative 2 times 2 is negative 4. 29 minus 4 is 25. Okay, so that's the square root of 25 plus 3 The square root of 25 is the number 5. And 5 plus 3 is not going to equal to negative 2. Okay, so here this one does not work out. So even though we had two possible solutions, it turns out x equals negative 2 is not valid. If you plug it in, you don't get an equation that's true. So here this one is extraneous. That one's thrown out. And so our only actual solution is going to be x equals to 10. All right. Now let's take a look at another radical equation. This one is just a little bit bigger because this one's going to have more than one radical inside. All right, so let's go ahead and try. All right, so let's go ahead and do this one together. We'll take the square root of x plus 4 minus the square root of 6 plus 2x, and that's going to equal to negative 1. All right, whenever you have one radical, what you want to do is you want to isolate that radical and then square both sides. We've seen that in the last two problems. You want to get the radical by itself, and once the radical is by itself, you want to square both sides. The problem here is that you can't do that because there's more than one radical. So if I move this one over here, okay, that one's been isolated, but now this radical is joined with this number. If I move this one over here, okay, then I've isolated that radical, but now this number and this radical are together. So no matter what I do, I can't get the radicals to be by themselves. So what we're going to do is we're going to handle these one at a time. We're going to isolate only one radical at a time because it's not possible to isolate them both. So here, I'm just going to pick one of my radicals and leave it where it is, take the other one and join it over to the other side. It doesn't matter which one we choose. We're going to do both eventually. So here, I'm just going to choose this one. And again, it wouldn't matter which one you chose. So I'm going to go ahead and add this over to the other side. That goes away. And now I'm left with the square root of x plus 4 is equal to, let's see, that's square root of 2x plus 6. And that's addition. It doesn't matter what order it's written in. And I'm used to writing my variables first. So let me write the 2x first and then the plus 6. All right, so there's my radical, and then I have minus 1. Just like that, right? So that one and that one are now together. All right, so now what I want to do is I want to square both sides. Okay, this side is simple. If I take the square of the square root of x plus 4, I just get x plus 4. No problem there. This side is going to be a little more complicated. When I square something that has multiple terms, I can't just square each piece. I'm going to have to multiply this out times itself. So let's go ahead and do that over here on its own. If I take the square root of 2x plus 6, and then on the outside of the radical I have minus 1, and I square it, that's going to mean I'm going to take square root of 2x plus 6 minus 1 times another copy of itself. Square root of 2x plus 6 minus 1. Okay, so now let's start distributing. If I multiply these together, a square root of 2x plus 6 times another square root of 2x plus 6, well, when I multiply something times itself, that's the same as squaring it. All right, that's what it means to square something. Multiply it times itself. Now, if I multiply these, negative 1 times that square root is going to be minus square root of 2x plus 6. You can write minus 1, although usually just minus is enough. If I multiply these, that's another minus square root of 2x plus 6. And negative 1 times negative 1 is positive 1. Multiplied everything out like that. Here, notice that I have a square root that's being squared. That's just going to give me the radicand. It's going to give me 2x plus 6. So that's going to be 2x plus 6. Notice I have minus square root of 2x plus 6 minus another square root of 2x minus 6. These are like terms. I can combine them. Minus one of these minus another one of these is minus 2 of these. And finally, notice right here, these are just regular numbers. I can combine those like terms. The 6 and the 1 make 7. So here that's going to be 2x plus 7 minus double square root of 2x plus 6. And that's what you get when you square square root of 2x plus 6 minus 1. So right here, if I square this side, I just get x plus 4. If I square this side, I'm going to get 2x plus 7 minus 2 square root of 2x plus 6. Okay, so now I have noticed that I've gotten rid of one of my radicals. I started the problem with 2 radicals. Now I only have 1. So we're going to do that again. Let's go ahead and isolate our radical. Let's get all this stuff over this way. So let me go ahead and subtract my 2x and subtract my 7, minus 2x and minus 7. That all goes away. And here I have x minus 2x is negative x, 4 minus 7 is negative 3, and that's going to equal to negative 2 square root of 2x plus 6. Just like that. Let me get rid of that negative 2 as well. Let me divide everything by a negative 2. Everything's getting divided by a negative 2. Okay. So here that's going to leave me just my square root of 2x plus 6. Over here, negative x divided by negative 2, well, that's going to become a positive, yeah? Negative divided by a negative is a positive. So I can write this as x plus 3 over 2. Negative over a negative makes that a positive. X over 2. Negative over a negative makes that a positive. 3 over 2. X over 2 plus 3 over 2. Okay, so x plus 3 over 2. Now that I've isolated my radical, everything else is on this side. Let's square both sides again. If I square both sides, the square of the square root of 2x plus 6 is just 2x plus 6. Here, when I square a fraction, I can square the top and bottom separately. If I square x plus 3, that's going to give me x squared plus 6x plus 9. If I square the number 2, that's just going to give me the number 4. Notice there's no more radicals now. This is a polynomial equation. Here, I still have a fraction, but that's just a regular whole number. So let me go ahead and multiply both sides by that whole number. Let me multiply both sides by 4. That way, I don't have to worry about fractions anymore. That's not required. You could deal with the fractions, but it's probably simpler just to get rid of them at this point. I don't want to have to deal with 9 over 4. Let me just multiply everything by 4. That'll give me 8x plus 24. All right, so there we go. So now that's a nice looking polynomial equation, and we can solve that. Let's go ahead and subtract our 8x from both sides. That goes away. And subtract our 24 from both sides, and that goes away. So that's going to give us x squared minus 2x minus 15 is equal to 0. And now that can be factored. That'll be x minus 5 and x plus 3. If x minus 5 is equal to 0, that means x is equal to a positive 5. On the other hand, if x plus 3 is equal to 0, that means x is equal to a negative 3. And these are our potential solutions. But again, we don't know if they work. You have to check these. Anytime you have a radical equation, you have to check for extraneous solutions. So let's go ahead and do that. Let's go ahead and check x equals to 5. All right, well, that's going to be the square root of 5 plus 4 minus the square root of 6 plus 2 times 5 is equal to negative 1. And again, all I'm doing is I'm taking my original equation, and anywhere there was an x, I'm going to go ahead and plug in a 5. All right, so now let's see what happens here. 4 plus 5 is 9. And the square root of 9 is just the number 3. Here, 2 times 5 is 10, plus 6 is 16. And if I take the square root of 16, I get the number 4. And here I get 3 minus 4 is equal to negative 1. Yeah, that's true. So here 5 is a perfectly valid solution. That works. Let's check the other one. If we check x equals to negative 3, that's going to be square root of negative 3 plus 4 minus the square root of 6 plus 2 times negative 3 is equal to negative 1. And let's see if that one works. 4 minus 3 is 1. Okay, that's fine. That's square root of 1. And the square root of 1 is just the number 1. Minus, let's see here, that's 3 times, negative 3 times 2 is negative 6, plus 6 is 0. And I know the square root of 0 is just the number 0. And so I get that negative 1 is equal to 1 minus 0. Or in other words, 1 is equal to negative 1. Yeah, that's definitely not true. So here, negative 3 doesn't work. This one's extraneous. And so we have to throw it out. And that is our only result. If you have square root of x plus 4 minus square root of 6 plus 2x is equal to negative 1, your only valid solution is x equals to 5. So go ahead and give this a try. Solve the equation, and don't forget to check for extraneous solutions at the end. Let's see. Let's have you try the square root of 8 minus x minus the square root of x plus 5 is equal to 1. All right. So go ahead and give that a try. And once you get a solution, and again, make sure that you've checked to make sure that you don't have any extraneous solutions, you can go ahead and unpause the video and we'll go through it together. All right, so here we go. We're going to go ahead and isolate one of our radicals. It doesn't matter which one we choose. I'm going to go ahead and move this one over. If you choose to move this one, it's all the same. All right, so let's go ahead and add the square root of x plus 5 to both sides. It doesn't matter which one you choose. I'm choosing this one mostly because it's got a negative. And if I add it over, I have one less negative to worry about. If I have the choice of choosing something that's going to leave things exactly the same or make something slightly simpler, I'm going to go with something that makes it slightly simpler. So here, that's going to give me square root of 8 minus x equals to 1 plus the square root of x plus 5. Or if you write the square root first and then the plus 1, that's fine too. It's addition. It doesn't matter what order you write it in. Okay, so now we're going to square both sides. Squaring this side is easy because you're just going to get rid of the square root. Squaring this side is going to take some more work. Okay, so 8 minus x. This one, all right, let's go ahead and do this off to the side. It's going to take a bit of work. That's going to be 1 plus the square root of x plus 5 squared. That's the same as saying 1 plus the square root of x plus 5 times 1 plus the square root of x plus 5. And now we start to distribute. 1 times 1 is 1. 1 times that square root is that square root. Again, 1 times that square root is another copy of that square root. And here, square root of x plus 5 times square root of x plus 5 is square root of x plus 5 squared. Something times itself means you're squaring it. But now here, that square and that square root simplify out to give me just x plus 5. So that's going to be 1 plus square root of x plus 5 plus another square root of x plus 5 plus x plus 5. And now I have some things that I can combine. Notice that x is the only x of its kind. Every other x has a square root around it. So that x is the only one that's like that. But here, these are both regular numbers. 5 and 1, I can add those together to get 6. These are both the same kind of radical. 1 square root of x plus 5 plus another square root of x plus 5 is 2 square root of x plus 5. So that's what we get when we square this. So over here, this side is going to be x plus 6 plus 2 square root of x plus 5. So now let's go ahead and isolate the other radical. Notice we've gotten rid of one radical. So now we're going to isolate the remaining one. Let's get rid of this stuff here. Let me subtract x and subtract 6 from both sides. And that's going to give me 8 minus 6, that's 2. Negative x minus another x, that's negative 2x. Those are both gone. And that's 2 square root of x plus 5. Let me get rid of that 2 as well. Let me go ahead and divide both sides by 2. Divide everything by 2, like that. And that's going to give me 1 minus 1x equals square root of x plus 5. There we go. So now we've isolated the only other radical left, which means now we can square both sides. If I square this side, I get x plus 5. If I square this side, I get x squared minus 2x plus 1. 1 minus x times 1 minus x will give me x squared minus 2x plus 1. Okay? Remember, don't just square each term. You have to distribute. You have to multiply 1 minus x times another 1 minus x. So now let's go ahead and make one side equal to 0. We subtract x and 5 from both sides. And now that one side is equal to 0, I can factor the remaining side. So this is going to be x squared minus 3x minus 4. And here, I could use the quadratic formula. I could complete and extract the square, but this one factors out very nicely, which is going to be the shortest way to do it. What two numbers multiply to give you negative 4 and add up to give you negative 3? That's going to be negative 4 and 1. Okay, so if x minus 4 is equal to 0, that means x must equal to 4. And if x plus 1 is equal to 0, that must mean that x equals to minus 1. Remember, these don't have to work. They're the only numbers that might work. You have to check them now. So let's go back and check our solutions. We're going to take these. We're going to take this equation right here and plug in these numbers one at a time into our equation. So let's take the square root of 8 minus, I'm going to start by checking x equals to 4. So I'm going to have 8 minus 4 minus the square root of 4 plus 5 is equal to 1. And let's see if that works. That's going to be 8 minus 4 is 4. And that's going to be 4 plus 5 is 9. Like that. The square root of 4 is 2. The square root of 9 is 3. And if I take 2 minus 3, that's negative 1. Oh, that doesn't work, does it? Because here we have negative 1 equals positive 1. Well, that's not true, which means x equals to 4 is not a valid solution. Okay, so here we throw that one out. That one's extraneous. Okay, so then let's check the other one. Let's check x equals to minus 1. If that one works, well, then that's the only valid solution. Oh, but if it doesn't work, that means we won't have any solutions. So here, notice this is false. And that's what makes this extraneous. All right, let's check this other one here. Square root of 8 minus a negative 1 minus square root of negative 1 plus 5. And that's supposed to equal to 1. Well, let's see here. Double negative makes that a plus. So 8 plus 1 is 9. 5 minus 1 is 4. Square root of 9 is 3. Square root of 4 is 2. And now 3 minus 2, that's going to be 1. Oh, okay, that one actually does work. That is a true statement. So here x equals to negative 1 is valid, and so it is our only valid solution. X equals negative 1 is our solution to our original equation. And that's the only one that works. All right, so now let's take a look at the last type of equation for this section. Let's talk about a absolute value equation. An absolute value equation is exactly what it sounds like. It's an equation that has one or more absolute values inside. So for example, let's say we have negative 3 minus the absolute value of x plus 8 equals to negative 4. That's an absolute value equation. An absolute value equation might have multiple absolute values, but it'll always have at least one. All right? With an absolute value equation, just like with a radical equation, what you want to do is you want to isolate your absolute value. You want the absolute value expression by itself, just like we had with our previous examples with radical equations. All right? You want the absolute value by itself. Just like you have here, you want to isolate the radical. All right, so let's go ahead and give that a try. Let's get rid of all of these expressions that get in our way. Let's go ahead and add 3 to both sides. All right, 3 minus 3 is 0. That's gone. And that's going to be minus the absolute value of x plus 8 is equal to negative 4 plus 3 is negative 1. And now I don't want that negative in front of my absolute values. I want absolute values just by themselves. So let me multiply both sides by a negative 1. That way a negative times a negative makes it a positive. So here I have the absolute value of x plus 8 is equal to negative 1 times negative 1 is positive 1. This is a very big mistake that I see people make all the time, and that's they will just drop the absolute values. They'll get to this point and they'll say, okay, x plus 8 is equal to 1. No, absolute value. An absolute value equation has solutions that a regular polynomial equation will not. It's not that it's going to give you totally wrong answers if you drop the absolute values. It's that you're going to be missing some answers. Right? Without the absolute values, this only has one solution. With the absolute value, you'll see it has more than that. All right, so let's go ahead and see what happens next. Remember what absolute value is. Absolute value is how far away something is from 0. So let's go ahead and we'll come back to the problem here in just a second. Let's go ahead and off to the side. Let's remind ourselves of what absolute value means. Let's say I have the absolute value of x is equal to 2. What that means is whatever that number is, it's 2 steps away from 0. So if you imagine your number line, and here's 0, the numbers that satisfy this equation are either going to be positive 2 or negative 2. They're the numbers that are 2 steps away from 0, either this way or this way. If I say the absolute value of x is equal to 5, well, same thing. It's the numbers that are 1, 2, 3, 4, 5 steps away from 0, and it doesn't matter what direction they're in. So whenever I have the absolute value of x is equal to 5, well, then I'd have 2 different solutions to that. Well, that's what I have here. I have the absolute value of something is equal to 1. And you say, well, yeah, but it's not just absolute value of x. It's absolute value of x plus 8. Well, that's true, which means we're going to have to deal with that 8 somehow. But this is still absolute value is equal to a number. And so whenever that happens, I know that the stuff inside the absolute values must either equal to the positive version of that number or the negative version of that number. If I say absolute value of x is equal to 2, that means x is equal to 2 or negative 2. X equals 2 and x equals to negative 2. I shouldn't say or, I should say and. Right? Both of these numbers work. Here, x is equal to 5, but also x is equal to negative 5. These are both valid solutions. So over here, if I say absolute value of x plus 8 is equal to 1, that means x plus 8 is either equal to positive 1 or it's equal to negative 1. Whenever you have an absolute value equation, once you've isolated the absolute values, this will split into 2 separate problems. Either the thing inside the absolute value will equal to the positive version of that number, or it will equal to the negative version of that number. X plus 8 will either equal to positive 1 or negative 1. And so now I can solve each of these on their own. Notice that each of these is a simple polynomial equation. I can subtract 8 from both sides there. and that's going to give me x equals to negative 7. All right, 1 minus 8 is negative 7. On the other side here, I can subtract 8 from both sides. And negative 1 minus 8, well, that'll be a negative 9. Just like that. But again, we have to check. With a polynomial equation, any number will work. As long as you've done everything correctly, your polynomial equation solutions are all perfectly valid. With anything that's not polynomial, radical, rational, or in this case absolute value, these might work. They're the only possible solutions, but we still have to check to make sure that we don't get anything extraneous. In later sections, we'll talk about other kinds of equations. We'll talk about logarithmic equations. We'll talk about exponential equations. We'll talk about matrix equations toward the end of the semester. In most cases, extraneous solutions are the norm. You're going to usually have to check for those. Polynomial equations are the nice exception. If your original equation was polynomial, you don't have to check. Otherwise, you probably do. All right? So let's see here. Let's go ahead and check these. Let's check x is equal to negative 9, and let's see how that works out. Negative 3 minus the absolute value of negative 9 plus 8 is equal to negative 4. Okay. Well, let's see. Negative 9 plus 8 is negative 1. So it's going to be negative 3 minus the absolute value of negative 1 is equal to negative 4. The absolute value of negative 1 is positive 1. Okay, so that's going to be negative 3 minus 1 is equal to negative 4. And yeah, that's fine. That's correct. Negative 3 minus 1, that's negative 4. So negative 4 equals negative 4, and that is perfectly valid. That is true. So here, negative 9 is a perfectly valid solution to our equation. Let's try negative 7. Just like that. Okay, so if we try negative 7, that's going to be negative 3 minus the absolute value of negative 7 plus 8. And that's equal to negative 4. All right, let's see if that's true. 8 minus 7 is 1. Now, of course, the absolute value of 1 is still just 1. So it's negative 3 minus 1 equals negative 4, which is absolutely true. Negative 3 minus 1 is, in fact, negative 4. So in this case, both of our solutions work out. They both check out to be true. And so this equation has two different solutions. None of them were extraneous. They both work out. Negative 9 and negative 7. Absolute value equations can be more complicated than this, but for the purposes of this course, this is meant as an introduction to absolute value equations, and all of our absolute value equations wind up with some nice linear expression inside. So, as our last problem for the section, go ahead and give this a try. Oh, actually, I take that back. That wouldn't be the last problem. We do have one more after this. So here, go ahead and give this a try, though. That's, let's do this one. Absolute value of 2x plus 1 is equal to 4 minus x, like that. So go ahead and give this a try. And once you have your solutions, make sure you check to make sure that they are valid. Go ahead and unpause the video, and we'll go through them together. All right, so let's give this a try. Here, we've already have our absolute values isolated. We don't have to get rid of anything. The absolute values are already by themselves. So at this point, we can already just split this into two separate categories. We can either say, okay, the stuff inside the absolute values, we can set it equal to the thing as it currently is written. In other words, take 2x plus 1 and set it equal to 4 minus x. Or we can take 2x plus 1 and set it equal to the opposite of this. Like that. Either equal to 4x, either equal to 4 minus x or to the negative of 4 minus x. And now we're going to solve each of these on their own. Okay, so let's see. I can go ahead and add x to both sides. This is linear, so here I'm not going to try to make one side equal to 0. Rather, I'm just going to try to isolate my x. So here that's going to go away. That's going to give me 3x plus 1 equals to 4. I can now subtract 1 from both sides. Makes that go away. And that'll give me 3x equals to 3. And finally, if I divide both sides by 3, that isolates my variable to give me x is equal to 1. And there we go. Same thing over here. First, let's start off by distributing our negative. That'll make things a little easier rather than to have an extra negative floating around. So that'll give us 2x plus 1 is equal to double negative makes that a positive x minus 4. We can now subtract x from both sides. Makes that go away. And that's going to give me 1x plus 1 is equal to negative 4. And finally, I can subtract 1 from both sides, and that'll give me x is equal to a negative 5. So this is another possible solution. So let's go ahead and give that a check. Let's go ahead and check these and see if they're both valid. Let's start with x is equal to 1. Let's check x is equal to 1. That's going to be the absolute value of 2 times 1 plus 1 is equal to 4 minus 1. And again, I'm just plugging the number 1 in for both of those values of x. So let's see, that's 2 times 1 is 2, plus 1 more is 3. And the absolute value of 3 is just the number 3. On this side, 4 minus 1 is 3. And yeah, that works out. The absolute value of 3 is definitely 3. So that is a perfectly valid solution. Let's check negative 5. X equals to negative 5. That'll be the absolute value of 2 times negative 5 plus 1 is equal to 4 minus a negative 5. Negative 5 times 2 is negative 10. Negative 10 plus 1 is negative 9. And the absolute value of negative 9 is just 9. Over here, double negative makes that a plus. So that's really 4 plus 5. And 4 plus 5 is just the number 9. So yeah, that one works too. So in this case, both of our solutions are perfectly valid, and we get 2 solutions to our absolute value equation. In a later section, we'll talk about absolute values in a slightly different context. We'll talk about absolute value inequalities, and you'll notice that it'll have a lot in common with what we see here. Okay, now, finally, our last problem. This brings us back to polynomials. You say, well, we've already done polynomials. Well, yeah, but every once in a while, we get a polynomial that's a little bit simpler to organize if we don't simplify it the way we usually do. For example, consider the problem (2x plus 5) quantity squared minus 6 times 2x plus 5 minus 16 is equal to 0. Okay. So let's start with that problem. Now, the very first thing I notice is that this polynomial equation is not simplified. Now, there's a lot I could do to clean that up. I could square this out. I could distribute the negative 6, combine like terms, and then factor. And that would be perfectly correct. I would get the correct answer. But I also notice that would be kind of difficult. It would take a while. I would have to multiply this out, combine terms, and then factor. And that's assuming factoring is even going to work. If factoring doesn't work, I might have to go through the quadratic formula or complete the square, which is going to add more effort to it. The thing to notice about this problem, though, is that I have a larger, more complicated expression that occurs several places throughout the problem. In this case, 2x plus 5 occurs here and here. Whenever you have an equation where you have a big, complicated-looking thing, and here it's not very big or complicated, but just as an example, when you have something that's more than just x that appears several times throughout the problem, here what we're going to want to do is we're going to want to substitute. This is not a different kind of equation. It's not like before where we said, oh, we're looking at radical equations or rational equations or absolute value equations or anything of that nature. These are still polynomial equations. It's not that we have a different kind of equation. It's that we're going to take our equation and we're going to think about it a slightly different way. This is called substitution. Not the equation, but the technique that we're about to use. It's called substitution. Substitution is a really useful tool in math, not just in algebra, but in really any math that you take, where if something is big and more complicated than just x, but that same bigger, more complicated thing occurs throughout the problem, you're going to take that thing and give it a separate name. Here's what I mean by that. I'm going to take the 2x plus 5 that occurs several times throughout my problem, and I'm going to call it the letter u. There's nothing special about the letter u. I could use any letter I like. I can use W, P, A. It doesn't matter what letter I want to use. The one choice you should not make is you should not use the letter x again, because x already means something in this problem. X means this variable. We don't want to call 2x plus 5 equal to x, because x is already being used. So it doesn't matter what variable you use, but do not use x again. Okay, so what do we gain by doing this? Well, what we gain is we can rewrite this problem by saying anywhere there's a 2x plus 5, I'm going to rewrite it using a simpler character. Instead of writing 2x plus 5 squared, I'm just going to write u squared. Instead of writing minus 6 times 2x plus 5, I'm just going to write minus 6u. And instead of, well, here, there's no variable, so let me just leave that as minus 16. Notice, operations did not change. Squares, minuses, multiplications, subtractions, those didn't change. Constants didn't change. That 6 and that 16 didn't change. All that happened is that this expression, 2x plus 5, we wrote it as something simpler. We wrote it as u. But now notice this I can solve by just regular old factoring. I don't need to go through and distribute and simplify, combine like terms, and then factor. I can just factor this thing on its own. Okay, well then that's going to be, let's see, what two numbers multiply to give me minus 16 and add up to give me minus 6? Well, that's going to be minus 8 and 2. Negative 8 times 2 is negative 16. Negative 8 plus 2 is negative 6. And so if u minus 8 is equal to 0, well, that means u has to equal to positive 8. And if u plus 2 is equal to 0, that means u has to equal to negative 2. Well, yeah, but the question wasn't solved for u. The question was solved for x. We were trying to find what value of x makes this equation true, not u. Well, yeah, but u and x are not totally unrelated. U just means 2x plus 5. So right here, if I say u is equal to 8, what that really means is 2x plus 5 is equal to 8. Right? If u is equal to 8, that means 2x plus 5 is equal to 8, since u and 2x plus 5 are the same thing. Likewise, if I say u is equal to negative 2, that's the same as saying 2x plus 5 is equal to negative 2. And now I can solve each of those for x. Here, let me go ahead and subtract my 5 from both sides. That's going to give me 2x equals to 3, right? Minus 5 and minus 5. And now let me divide both sides by 2. That's going to give me 3 over 2. The original question was polynomial. I won't have any extraneous solutions. As long as I did everything correctly, that solution I don't need to check. Radical equations can have extraneous solutions. Rational equations can have extraneous solutions. Absolute value equations can have extraneous solutions. Polynomial equations do not. So here, as long as we've done everything correctly, that is a solution. Over here, I can do the same thing. Let me subtract 5 from both sides. That'll give me 2x equals to negative 7. Negative 5 minus 2 is negative 7. And then let me divide both sides by 2. It's going to give me negative 7 over 2. And there we go. These are my solutions. Note that substitution is not a separate type of equation. It's a technique that's used to simplify the equations that we've already seen. Right? As you're going through your problems, you will occasionally run into some problems where you're going to have to simplify or factor out an expression. If you ever see something that's more complicated than x, but that appears several times throughout the problem, you may consider using substitution to solve. Right? So that is it for the section, and that is it for all of these kinds of equations. I know this is a bit of a long section, but it is the longest section that we'll be having in this course, mostly because of all the different things that were in it. If anybody has any questions, comments, or problems, please make a note of them, write them down, and you can email me. You can talk to me during our next meeting. You know how to reach out to me. So please let me know, and I hope everyone has a nice day.